Hello guys, my name is Diego Pacheco and this is another slidecast. So today we're gonna continue talking about security. Particularly, this will be a video about encryption. This video gonna be heavily dependent on Java, so you also can consider it as a Java video, all right? So I hope you guys like it. So let's get started for the slidecast. So the slidecast is called Encryption Deep Dive. We're gonna talk about the problem space, and also we're gonna talk about Java. So this is encryption in the context of Java. If you remember my previous slidecast where I have a similar image where I have a bar and lots of key locks there and was saying that was wrong, in this case here is completely right, right? Because when we are talking about encryption, every keypad here means you have a different key. And then that's the right thing to do. You want to have key diversity, you want to have more keys because that reduces the blast radius on an attacker surface, right? So although the last video, the image I was saying that was not proper, for this one I believe is very proper, right? So let's get started. If you didn't watch my previous slidecast, I recommend you do. It will not block you to understand any of the things I'm gonna talk about it today, because this will be more focused on encryption. However, if you are interested in security, and I think that's something you should be learning more, no matter if you're working with DevOps or not, that's a video where I kind of cover the landscape in a more broader sense of it. So here's the link. You can look on my YouTube channel or on my blog. You're going to be able to get there. All right. So let's talk about asymmetrical encryption. On the previous video, I also talk a lot about it. So today you're going to be very briefly, this whole video going to be more towards symmetrical encryption, right? So the idea here is like, let's say this is like classical security where you have Bob and Alice exchanging messages. So Bob sends a message, hello Alice, he encrypts with his public key, then he gets a ciphertext, then Alice can get the ciphertext and he can decrypt with her private key, and then you get your plaintext back, right? So asymmetrical encryption means you have two keys, both keys doing encrypt and decrypt, but often one do encrypts and another does decrypt. We do that to protect data at transit. We also call it public key cryptographic. Public key does encryption, private key does decryption, like was mentioned before. On the previous video, I was explaining more detail if you want to know how TOS work and MTOS, but that's definitely used by that, and you're gonna see in any server who has HTTPS, which should be the default nowadays. Also for SSH, if you are, accessing a Linux machine or on the cloud like AWS or Google, wherever. And the most used algorithms are RSA, Diffie-Hellman, and elliptic curve, right, which is called ECC. And often the key sizes, they change from 1 to 4 kilobytes, right? That's all we're going to talk about asymmetrical encryption. And now just let's talk about symmetrical encryption, the whole slidecast. So symmetrical encryption is used to protect data at rest. Let's say if you have a payment software, or if you have PII, personal identifiable information, you would use symmetrical encryption. So here again with Bob and Alice, Bob writes, hello Alice, that's Bob plaintext, we encrypted. Then we have ciphertext, and then now in order to Alice to decrypt it, Alice needs to have access to the same secret key, and then Alice can see the plaintext message, hello Alice. So this requires some entropy, and that can be done with RNG or PRNG, which we're gonna cover later on. It's just number generators or secure number generators. ideally when you are in Java. One of the biggest problems we have here is to access the key, because you need to share that key and you need to share it in a protected way, right? So that's one of the biggest problems on the problem space. We also have different algorithms, like there's block algorithms and there's streaming algorithms. Although stream might sound better and block, because you might think about blocking, it might sound worse. It's actually the other way around. Block is more secure. Some of the algorithms, AES, which is the biggest and famous one, RC4, RC5. RC4 and RC5 are streaming algorithms, and AES is a block algorithm. The key sizes, if you remember about the symmetrical ones, they vary from 1 to 4K. Here's much smaller, is from 128, 196, or 256. And I need to splash some sort of a math here, right? Otherwise, but this is the worst math you're gonna see here. It's just some silly functions, right? So what you want to do is to have ciphertext, right? Which means what Bob did. And in order to have ciphertext, we have this function called E, and E stands for encrypt. And then you have two parameters. You have K and P. And K is the key, the secret key, and P is the plain text. And if you call an encrypt function passing a key and ciphertext, of course that function is gonna use an algorithm, and then you're gonna get a ciphertext. And we also have the other function, which is called D for decrypt, where you're gonna pass a key named K and a ciphertext, which is gonna be called P, and then you're gonna get a plain text back, right? That's the most advanced math you're gonna see. The other ones we're gonna be just fine, so no worry about it. It's still talking about symmetrical encryption, some things that happen under the hood, right? So ciphertext is either the same length as the key, or is slightly bigger than, sorry, not the key, the plain text, right? So either the ciphertext is exactly the same length of the plain text, or the ciphertext is slightly bigger than the plain text. But by any means, the ciphertext never should be smaller than the plain text. So under the hood, what happens is permutations, right? And they should be determined by the key. So what should rule the permutations? Of course, there are some algorithms that behave a little bit differently, and we're gonna cover that. But mainly is the key driving the permutations. Different keys should result in different permutations. And that's the part where sometimes people confuse encryption with hashing, because if you hash something with the same data and the same function, you always get the same hash. Here, even although you use the same key, you're gonna get a different ciphertext, right? You might see some data in common, which is that what you want to avoid, and we're gonna talk about that later on when we talk about operational modes. But long story short, the permutations, they should look random, right? They should not look predictable by any means. And what I'm talking about is a very old cryptography principle. I'm not sure if I'm gonna pronounce this correct, but it's Kirchhoff's principle, which is from 1883, and it relied with the idea that a secret key, not on the secrecy of the cipher. So actually you might know the cipher algorithm that might be public and that may be fine. So you don't secure things by providing obfuscation or hidden things. You secure things by the secret value of the key. That's how you provide secrecy, right? So you base it on the secrecy of the key, not the secrecy of the cipher, because anyone can break the cipher. But the idea is like, as long as people don't get the key, it should be totally fine. And also we need to talk about storage level and application level in encryption. So storage level means you're gonna store transparently in your database. Every time we're doing encryption, we have a side effect, which is affects performance, right? Is a fact that you're gonna have performance penalties. And if you go storage level encryption, you have transparency. However, it's less secure than going with application level encryption. But application level encryption, although is much more secure, it has some drawbacks, and let's see these drawbacks. So one of the drawbacks, it requires engineering discipline, right? Because since this is not encrypted by the database layer, is encrypted by the application using SDK. If the engineer forget to call encrypt on that piece of data, you're gonna have unencrypted data in your database, right? And that might create trouble for you. Maybe not. But if you go back to storage level encryption, the engineers don't need to do anything, and they cannot work around it because it's done on the different layer, right? So one of the drawbacks is it requires engineering discipline, and if you sleep on this, you might found an encrypted data. You might need to deal with it later on. It also requires constant education and training. As you change your standards or as you evolve, people need to know what to use, how to use it. If there is sort of a spec, they need to know the spec, the guidelines. If there's a library, they need to use the library. The library needs to be up to date. So there's some sort of ongoing training that never ends, which is not necessarily bad. Don't get me wrong, just some fact of it, right? I think the worst problem for me is it cripple features, right? So if we think about a relational database, often you can get a primary key, or you can get an index on a column, and you might want to do that so you can get uniqueness. Let's say you don't want to have two different roles with that same piece of data. And with application side encryption, uniqueness get tricky, because then uniqueness only gonna work if you have the exactly same ciphertext, but you might never ever get the same ciphertext. If I encrypt John 300 times, I might get 300 different ciphertexts, so they will be all unique. So I'm gonna break uniqueness, which is something you had almost for free before, right? Also, join is gonna be a problem, because if you do a join into different ciphertexts or the same ciphertext, the problem is as you rotate that data, that ciphertext is going to change, and then all your joins is going to break. So you need to factor your app, or do some sort of a lookup, or do something smarter to do your joins, but you cannot do them directly anymore. It's a problem. So you need a level of indirection there. And you also have search problems, right? Because the ciphertext is not plain text, so you cannot do anything but exact match. You cannot do sub match or partial match or full text search. All right, so you're basically losing some search capabilities. And for me, that's our sort of the biggest problem with application side encryption or application level encryption, because you cripple some of very common engineering techniques. And also, as say you have bugs or changes or improvements, this will require migrations, right? Because as you have SDK, you might need to go there and all your microservices and roll out the changes. So this might be a source of endless migrations going on. And also some interesting aspect of it is also when we think about key diversity, like let's say I have one key per application, or I want to have one key per microservice. This actually is not defined by my sole will of having more keys. This is defined by something called Conway's law. So in architecture, we have this principle from called Conway's law, which says that the software that we're gonna build gonna reflect the communication structures our organization gonna have. So if I have a team that has access to 10 keys, very likely that my software gonna have to provide access to that 10 keys, right? And if I say that I want to have one key per user, if I don't change maybe my team structure in the way that my team work, I might not be able to change my architecture, and I might not be able to change my security scheme. So basically, one thing is reflected by another, right? So the key scoping is a mirror of the architecture, and the architecture is the mirror of the business themes structure, and there's an amazing book about that called Theme Topologies. I highly recommend you guys take a look. All right, so this is something really, really important to keep in mind. Right, so it's in the way that key scoping works, you need to think about your themes and architecture first. Otherwise, you might not be having any choice to do that. And that's just another drawback of application-side encryption. Talking about protecting the keys, which is one of the biggest challenges with symmetrical encryption and asymmetrical as well, you have some options, right? So either you store the keys, the key material on a hardware token, something like a smart card or USB dongle, or you have some sort of a on-the-fly generation, can be from a password, or you can protect the key with another key. So you can wrap that key with another key. You can use a key to encrypt key. That's often known as KEK, key encryption key. There's an interesting concept I'm gonna talk later on at the end of the slidecast, which is envelope encryption. And one thing that pretty much all cloud providers have nowadays, if you look about AWS, Google, Azure, they have KMS systems, which is key management system, where they have software that can manage these keys, manage these keys for you. And we're gonna talk a bit more about this one in AWS later on as well. So in encryption is all about randomness, right? And a probability of a distribution. So randomness is just the probability of some distribution, right? Complaining about my own pictures, like that dice there on the top is really bad, right? Because you don't have many possibilities to happen there. So it's a very bad one. So probability is about also likelihood of something happening. So we can say that binary putting 0 means something never gonna happen, and 1 meaning for sure it's gonna happen. So I have full certainty that's gonna happen. And in probability, when we have a uniform distribution, it means that all probabilities are equal chances to happen. That's a uniform distribution. So for instance, if I toss a coin, I have two possibilities, right? It can either be a tail or a head. So this can be expressed as 1 over 2 plus 1 over 2 equals 1, right? And you have one of two chances of head and one of two chances of tail, right? In encryption, we also need to talk about entropy. Entropy is a very common term, right? And it can be seen as a measure of uncertainty, right? So this means that you can also see this as a measure of disorder on a system. Uncertainty is seen as chaos. And entropy is the amount of surprise that you're gonna find on a result of a random process. So, like I was saying before, encryption is about randomness and entropy. So when you see a ciphertext, you don't want to see common things between ciphertexts. You want to have surprises all the time. Otherwise, you might be easily able to predict what's going on, and you might be able to break that cryptography, right? So that's all. You want high entropy, high chaos. You don't want to be able to predict anything there. And higher entropy means less certain to find the result, so less predictable, and that's what you want. I found this picture I find quite cool, where you have arrows for all directions, so you don't know exactly where you're going. So you want to get as more noisy as you can there. So entropy is also maximized when the distribution is uniform, right? So you have all equal probabilities of anything happening. Because if you have less probabilities, you might be, deviation to one thing that might happen often, and you have less randomness there, right? If you think about it, it makes sense. So with that, we can talk about something called RNGs. And RNGs are random number generators. So they are also a source of uncertainty. So they are a source of entropy or randomness, right? And a crypto algorithm, which is high quality, needs to have high quality bits from the source of entropy, right? It's really a big deal in encryption. So RNG should be sampling from sources of entropy. There are several sorts of entropies. Just to name a few, it could be measures of temperature, acoustic noise, air turbulence, electric static, which is not always available. So you might be getting some entropy from your underlying operational system, such from sources like sensors, I/O devices, network, disk, logs, running process, but this can be fragile and manipulated by the attacker, right? So you need to pick this very carefully. But ultimately, you can see that RNGs are sort of analytical. And then PRNGs, which is P stands for pseudo. So pseudo random number generators, they need a RNG product. So they use a RNG source, which is analog, but they are slow, and they are not deterministic, right? And they not guarantee high entropy. And what we want with a PRNG is to have something that looks random data, but is generated very quickly from digital sources, and they're deterministic, and they should have maximum entropy, right? So you use a RNG to generate a PRNG, so you have something stable and fast and full of entropy, meaning full of chaos, full of unpredictable things. And PRNGs, right, in order to be secure, they need to ensure two properties. They need to ensure backtracking resistance. So previously generated bytes are impossible to recover. And they also need to protect prediction resistance. Like it should be impossible to predict future bytes. In Linux, we have these two sources of PRNGs. We have dev random and dev urandom, and the difference is random is blocking, urandom is unblocking, and there's some holy wars here. Some people defend random is better, others defend urandom is better. So there's all sorts of different opinions here. And in Java, what you want to do is to use a secure handle. And under the hood, you might be relying on dev random or dev urandom. That's what's going on. So now, let's talk about algorithms, right? So when we're going to do symmetrical encryption, we will use an algorithm. And the most used one is called AES, which stands for Advanced Encryption Standard. This is really the world de facto standard for encryption. NSA approved it. They use it for top secret information. Although people, relate AES with Americans, is actually Belgian, was created in Belgium. It's more Belgian than American, actually. Funny fact. You have blocks of 128, 192, and 256 bits. That's the key size. You can assume that AES is never gonna be broken. And just to give you some perspective, all input bytes depends on output bytes in very complex pseudo-random way. Talking more about AES, you might be wondering, how do you know if this is secure? How people know? Basically, they have these hackathons with cryptographers where they let the algorithms out there and wait to see if people can break it. And I think they run this for more than 10 years. And what they got was something like this. In 2011, people found a way to recover, but this was a 128 bits key. And remember, you can make it up to 256 bit key. But this requires an insane amount of ciphertext, right? Pairs of 2 on 288. So really, we don't need to worry about this. So the biggest threat is not on the core algorithm. AES is completely safe and sound. What you need to be worried is how you use the operational modes. That's where you might be in trouble. And we're going to talk about that in a moment. And these operational modes, they have sort of two flavors. The ones that you might use for authentication and the ones you might use for confidentiality. We're going to focus here more on the confidentiality ones, but I'm going to list them for you. So these are the AES operational modes. So besides the core algorithms, there's this specific difference you're going to see. So for authenticated encryption, you're going to see GCM is very common nowadays, CCM, SIV, and AES, GCM, SIV. For confidentiality, we have ECB, CBC, PCBC, CFD, OFB, and CTI. So let's see some of those. So the ECB, which stands for Electronic Codebook, works like this. So you have your ciphertext, you have your block cipher for decryption, and you put the key and you get a plain text. And then you see that the same happens for the other blocks, and you see no retrofit, no feedback, right? And that's sort of the problem with it, right? And there's this classical thing you can find on the internet where this image was encoded with ECB, and then you can look here that was poorly encrypted, and you can almost see the whole image, right? So I think this gives you a hint that if you're doing regular encryption, ECB is not safe. You should not do it, right? To fix that, there's a different operational mode called CBC, which stands for Cipher Block Chaining. And the idea here is you have feedback. So the blocks, they're not independent anymore, like in EBC. They are chained, right? And what we see here, there's two differences. We see there's an initialization vector called IV. And at the end, we see that the ciphertext is used as input to the plaintext, and there's a shor operation going on here. And we see that for each block, right? So this is much more secure. However, you make sure that you use a good sense of entropy and randomness on the IV, because that, if you use the same everywhere, you might be putting yourself up to a dictionary attack. So there is a variation of this one called Pcbc, which is called Propagate Cipher Block Chaining. And here we have a very small change. The initialization vector here you see is using after the encryption of the first block. And the shor now is used both plaintext and ciphertext. And that's sort of the difference between CBC. This is not widely used. I think this is used on Kerberos 4, but it's not used in Kerberos 5. But CBC is quite used a lot nowadays. There's this other one called CFB, which stands for Cipher Feedback. This is a string cipher. This is not for confidentiality. What we see, which is interesting here, is that, well, the encryption is a blocking operation. You need to do block by block sequentially. And we see here the IV goes into the cipher encryption function. And we can see there is a shor with the plaintext and the result of the ciphertext. And that goes carry on to all blocks. That's why it needs to be in parallel, because you need the previous ciphertext block in order to encrypt the next one. However, for the decryption, look how interesting this is. You use the ciphertext, and the ciphertext is the same. So the shor is between the ciphertext and the plaintext, meaning the decryption can happen in parallel. The encryption is sequential, but the decryption can be in parallel. So that's something interesting about this operational mode. We have another one called OFB, which is very similar. This stands for output feedback. Again, is a string cipher. However, here, what we have here is the encrypted IV is shored with the plaintext, and that will produce this effect where you do not require padding data. And here we can see the schema. We can see that IV is sent to the block cipher encryption block. We can see that the plain text is shorted with the cipher text, and that happens everywhere. But then we can see plain text on each block now on. And also for decryption, we can see IV again on the cipher encryption block, and we can see a short between that block and the cipher text, right? And finally, we have CTR. So the cool thing about CTR is that both encryption and decryption can happen in parallel. And the reason why you can see this is if you look at these pictures, they don't have retrofit. What happens actually is they have a nonce. Nonce it stands for number used only once. So it's like an IV, but I personally prefer the name because I think the name makes more sense for me, because you are enforcing to say, hey, use this number just one time, don't use it everywhere. But it's exactly like an IV, is a nonce. But the cool thing here, what happens, like you have this counter that's incremented on every block, right? So it's predictable, and that's why you can do it in parallel. You can know how many blocks you're gonna have. And if you look this diagram, you see there's no feedback between blocks. That's why everything can be in parallel, both encryption and decryption. So that's CTR. Now, let's talk about Java, and let's see some code. So in Java, first thing we need to figure out is how to create a secure handle number, right? So Java has some algorithms you can use. There is native pseudo random number generator, or PRNG. There's native PRNG blocking. There's native PRNG non-blocking. There's PKCS S11. There's SHA-1 PRNG, and there's Windows PRNG. So from bottom to up, Windows PRNG, if you are using Windows, SHA-PRNG is the default, right? PKCS11 uses your PKCS11 library. And the difference between PRNG blocking and non-blocking is that non-blocking uses /dev/u random, and native PRNG blocking use dev random. Of course, that's depend on your OS. So in Java, in order to create a secure handle generator, and see that here I'm using the word secure because in Java you can use handle number generator, but they're not secure, so don't use them. For encryption, use a secure handle number generator. So here we are creating that for us. So what we are doing is I have this class where I call it secure handle generator, and there is a generate method where I first get access to the algorithm. So I do secure handle.get instance. I'm using native PRNG. Then I have an instance of a secure handle. We might receive a no such algorithm exception. That's why you see a try catch there. And then I can get my IV, or my nonce, right? And that's our 16 bytes block. So I get that byte array in memory. And then I ask for next bytes. Next bytes will fulfill that array with random numbers there for me. And then I return that. And here on the main, I just printing, because this is an byte array, I need to encode it with base 64, which is going to make it more or less 33% bigger, with also there's padding. So we can visualize it. Otherwise, you're just going to see random bytes there, will not make more sense, right? But here, if you take a look here, this is going to be bigger than 16 because of the base 64. So here I just printing my secure handle generator.generate and just encoding on base 64. So just for visualization, right? And you're gonna see something like that. Every time you run, you're gonna see a different number, right? Now let's see how can we generate cryptography keys, symmetrical keys in Java. And by the way, I'm just using Java standard JDK. There's no libraries here. That's the cool part. Even for the secure handle generator, this is all standard Java SDKs, JDK. So here I have a sample key generator, and I have a method to generate a 256-bit key. You can see I have no parameters because I want to get this right, so I just do whatever I need for the user. So here, you also need to get an algorithm, which we're going to use AES. Then I want to init the generator, meaning I need to say what's going to be the size of this key, 128, 192, or 256. I want to do 256, of course. Then I call generate key, and I return that. And here we have some main application on the bottom, where I'm printing the key. Again, a Java key is just a byte array in memory. So it's just entropy bytes, random bytes in memory. That's what a key is, right? So to splash that would be a bit weird. So I am using base 64 to encode it. Again, going to be 33% bigger plus padding. And I'm wrapping on a string. And you're going to see something like that. So that's like the string base 64 representation of my key. Of course, I'm printing the key here just because I want to show you guys how you do it, but you need to keep in mind that you don't want to print your key material. That's a security problem you're going to have, right? So this is just for testing and educational purposes. And here we can see how we can encrypt using Java. So now is the time where we're going to use our operational modes, if you remember what I said in a moment ago. So here I create this class, I call it Encryptor, and Encryptor has a method called Encrypt, where I receive my plain text, my secret key, and my IV. And what we do, again, just standard Java JDK here. So we create a cipher, which is a cryptographic word for algorithm, right? And then the cipher, look here, I have AES, but I have /CBC. So my operational mode is CBC, and I have something else, which is I'm specifying if I want padding or no padding. In this case, I want padding. If I was doing no padding, I would need to have the plain text be multiples of 16. Otherwise, I need padding. So I don't know the size I'm going to get, so I'm going to do padding. And then I'm going to get a key, all right? So in Java, you have this secret key spec, and you just instantiate it, and you pass the key. When we have this method where I do key.encoded, that just return a byte array. And the name of algorithm I'm going to use with this key, which is AES. And then I get my IV, because remember, CBC has IV. And then I have IV spec, which I'm going to initialize it with my IV. As you can see, just a byte array there. And then I initialize the cipher saying what I'm going to do. I'm going to do encryption, so I do encryption mode. And then I pass the spec, which is the key, and the IV spec, which is the IV. And then I can do cipher do final, which means execute the algorithm. And I'm passing the plain text. However, I need to pass this as byte array. So that's why you're seeing this plain text, which is a string. You see this get bytes, and I need to pass an encoding. So I'm passing UTF-8 just to be fine. And finally, I'm going to get a byte array with the ciphertext. However, I want to return this as a string to be nicer for the color. So I'm already encoding with base 64, and that's it. And here we can see a main application in order to encrypt. So first thing we do, we're going to use our previous code, and we're going to use the simple key generator in order to generate 256-bit key. Then I'm just printing the key. Again, you should not do that. Don't print your key material. Don't log it. This is just for educational purposes. So I also need to use base 64 to encode the key because it's a byte array. Then I'm using my secure handle generator, remember, or PRNGs, and I'm generating an IV or nonce, right? And I am also printing. Again, don't print your IV. That's just because education. And finally, I can encrypt. And then I do encryptor.encrypt. I pass my message. So I pass, this is a test message, exclamation point. Then I'm passing my key and my IV. And you're going to see something like this. You're going to see key, some value like that, IV, some value like that, and ciphertext, some value like that. Again, don't comment those. I'm just doing that for education. Now, let's see how can we decrypt in Java. So I create this other class. I call it Decryptor. and I receive a ciphertext, secret key, and IV. Then I need to get the cipher again. It's exactly the same cipher. I get the spec, exactly like I did before. Now I need to decode it with base64, because remember, when we passed the key was encoded. Now I need to decode it. That's why you're seeing a decoder here. Then I need to create the IV, but again, I need to decode the V, because remember, the IV is encoded as well. And now the cipher.init, I need to use decrypt mode instead of encrypt mode. I still pass the spec, which is the key, and IV spec, which is the IV. Then I do cipher do final to get the plain text. However, I also need to decode the ciphertext, right? Because it's encoded with base64. And this is going to give me a byte array with the plain text. But I also want to see this as a string. So I create a new string, UTF-8 as the full char set. And that's how we got it. Finally, let's see this on a main class. So we have a secret key. I'm importing my previous key. And to do that, it's very simple. I just create a secret key spec. And I pass my key material there. Right? Again, you don't want to do tests with your production key material. That's just for educational purposes. Then I need to get that as bytes, right? And that's what we do. That's why we see a string dot get bytes. And that's how we got our secret key. And here's our IV. IV is just a string, but again, I need to get as bytes. So I get our IV material there, and I just do get bytes. And finally, I call decryptor.decrypt, and then I pass my ciphertext, and I pass my IV and my key. And this is how we decrypt. So now let's talk about more keys and data rotation, or keys and data rotation, right? So the use cases for this is a very common practices in security to do regular rotations, right? You want to regularly rotate certificates and key. That's an industry practice. And you want to do that because it's a regular thing to do, or because you got breached, right? Let's say you got an invader, you clean your systems from the invader, and then you want to protect your users' data again. So you want to rotate the data. So like I said, this is a standard industry practice. This might vary from vendor to vendor, from tool to tool, from company to company, but in average, there's a common sense that people want to do that in every 90 days. There's two ways you can do it, with downtime and without downtime. I also, for my Brazilian friends, we can say this with emotion and without emotion. So, or it is more like translated in English as adrenaline or something like that, because with downtime, of course, it sucks for the business, all right? However, it's more simple, right? Because you don't have race conditions and you don't have applications doing read and write at the same time as you are rotating things. With no downtime, yes, it's better for the business, but for you it might be a bit more challenging because you might have some race conditions there. This can have reliability implications, because when you are running rotations, if you cannot write data, or if there's a race condition there, when you are rotating someone, change that data under the hood, you might need to retry it, or you might need to try again later on. So there's some implications here. You're also gonna need some sort of a data catalog, because you need to know where your encrypted fields are, assuming that your database has mixed tables with encrypted and unencrypted. Some companies, especially on a big data landscape, what they do is they sort of have different schemas. So this schema is my encrypted data, and this schema is my non-encrypted data. In that case, it's much easier, because then you just get one particular schema. But if you don't have that, if you have mix and match, you might need a catalog in order to figure out which ones to do and which ones to skip it. And this also has other challenges for operationability, observability, and rollbackability. Operationability, I mean, how are you gonna run this? Do you want to create a Jenkins job? But what if this thing broke in the middle, can you continue where you stop, or how to make sure this process doesn't stop until finished? So that's operationality challenge. Observability challenge is, how do you know that you are doing the right thing? How do you know that you are not corrupting any data? And rollbackability is, can you roll back if something goes wrong? And how do you know something is wrong, or can you really hold back? Because if the data is changing under the hood, if you hold back it, you might create some sort of a data resurrection issues, right? So this is quite challenging, actually. Now is the time for us to talk about envelope encryption. So envelope encryption is more secure. You're basically using more than one encryption key, and that's a industry standard. And you basically encrypt keys and data, and you can have as many levels. You can see this as like Russian dolls, right? So you have a key that encrypts the key, that encrypts the key, that encrypts the key. Depends how many levels you want, from, I don't know, 2 to 4 or 2 to 10. And then finally somebody encrypts the data, right? So you keep putting things one inside another. So it's like a Russian doll scheme. You are encrypting keys, metadata, data, whatever your envelope has. However, you have a bootstrap problem. What happens with the first key, right? Who is protecting the first key, and or the master key or the root key, right? So that key often is protected by a KMS solution, which is what we're gonna cover right now. So in AWS, we have AWS KMS. KMS stands for Key Management System. Although we're gonna talk about the AWS here because it's the cloud provider who I'm mostly aware. I also very aware and worked a lot with Google, but I'm covering AWS here. But Azure and other providers also, they have KMS solutions. And so in AWS, KMS is the security solution on the cloud. Under the hood, you use it something called HSM, which is stands for Hardware Security Module. Is a backed by hardware solution to secure and protect your keys, your master key at least. Your master key in AWS is called CMK, or customer master key. In AWS, there are the keys never leave AWS, right? So you never can get access to your master key. It's important. It's possible to import your key material on KMS, but once you import it, you cannot get it out. There's no way to export it. You can delete it, CMK there, but it's pretty hard. It's not right away. It's not atomic, and there's some protections, right? So basically, you never have access to the KMS CMK key. And this is what makes it secure, right? Because if you don't have access to the key, it cannot be leaked, and if it cannot be leaked, it cannot be wrecked, right? So it's much more secure. And with KMS, the only problem is that all encryption is remote, and remote is lower by nature because you need to move the data to the encryptors and decryptors rather than the other way around, right? AWS has some interesting things they're doing to make this faster. They did some interesting stuff on S3, and I think this will get better. But you need to keep in mind that although KMS is very secure, is remote encryption, right? And that might be slower. So with KMS, you can do symmetrical and asymmetrical encryption. This is also integrated with IAM for permissions. This is stored on KMS side. And also you have several other services on AWS that have support for KMS, like EBS, this is used for volumes, S3, Kinesis, Redshift, right? And I believe as the time passes, we're going to see more AWS services using KMS. KMS is also integrated with CloudTrail, so you have an audit log where you can see what's going on. And here's a very, very simple way to see what's going on envelope encryption. You have a master key called CMK who never leaves KMS. That key encrypts the data key. The data key can either be generated by you or generated by AWS. If you call KMS, there's a remote operation to generate the data key. And then you also can send your data to KMS, and KMS can encrypt for you. But there's a limit of 4 kilobytes to do it. But for the key, it's fine. You're going to have like since this is symmetrical encryption, I'm going to have 128, 192, or 256. And then with the data key, you encrypt the data, right? Another way to see envelope encryption is like this, right? So your master key, which is the CMK, you're gonna use that in the data key in an algorithm, right? So the master key, you're gonna encrypt the data key, and you're gonna have the encrypted key. The data key is gonna be encrypted. That's why we see the green key with the red padlock there. And then you're gonna use the data key in your data in an algorithm to encrypt your data. And then in your database, yes, you heard it right, I said in your database. So you're gonna store both the encrypted data key and the encrypted data, the ciphertext, alongside with your data on your database. And doesn't matter what database you have, if it's Mongo, if it's Elasticache, if it's Redis, if it's Dynamite, if it's RocksDB, if it's ES, if it's S3, if it's Aurora, if it's Redis, it doesn't matter. Postgres, MySQL, whatever. So envelope encryption means that in your database you have your data encrypted and your data key encrypted. And the good thing about that is the fact that you cannot lose the keys, the data keys, because in order to lose the data keys, you need to lose the data. So that's the cool thing about it. And you should be thinking, okay, but wouldn't the attacker be able to read this, reading my data? No, because your data is encrypted and your data key is also encrypted. Okay, but then how you read it? Well, that's the time where you need to do the remote encryption, and then you call KMS and ask KMS to decrypt the data key with CMK, and then with the decrypted data key, you can decrypt the data. And that's how you roll. So some books, if you guys want to learn more, there's this awesome book called Serious Cryptography. It's really, really good. For Java, there is Java Cryptography and Java Security as well. And there's this also this other book called Web Application Security, which is also a good book. So that's it for this slidecast. I hope you guys like it. See you next time. Take care. Cheers.